Welcome, everyone. I'm very happy to see you all here for this Heidelberg AI event. It's actually our first in-person event since quite a while. We have done some online events, but we're happy to be here again, and this time, with you, Lynton. Thank you so much for giving this talk on uncertainty quantification for LLMs. Very nice. I'm gonna really quickly tell you something about Heidelberg AI if you don't know us yet. So we are a non-profit group that is trying to foster collaboration among AI people in the region, and we're here embedded with some of the local partners, with the Alice unit Heidelberg, with the Data Science Seminar, and especially the DKFZ, which offers us also lots of access to the infrastructure, like here, the room, and so we're very grateful for that. This is our current organizing team, and also for those, for the DKFZ grad students, actually for this event you can, credits for this event can be given. For this you can contact Doreen if you would like to do that, and yes, we will have about 15 minutes talk with a discussion in the end. And yes, now I'm gonna present you real quick. Sorry for being in the way. But Lynton finished his PhD in 2023 in machine learning at Heidelberg University in the Goethe lab, and where he developed deep generative models with built-in uncertainty quantification for inverse problems. His thesis on conditional invertible neural networks was awarded with the Ruprecht-Karls Prize. And his methods have found applications in medical imaging, astrophysics, particle physics, and mechanical engineering. And yes, from 2022 till 2025, he was head of machine learning at CoPresence, an AI startup for 3D avatar reconstruction. And now he works as an independent researcher, helping startups and smaller teams to assess feasibility and prototyping and make technical decisions around AI. Thank you so much for being here and giving the talk. Please give an applause for Lynton.
Okay, uncertainty quantification for LLMs. I want to start with one of these would you rather scenarios. So imagine a genie comes to you and offers you a choice of 2 magic potions. If you drink the orange potion, any machine learning model you interact with magically has a 3 times lower error rate. And if you drink the pink potion, any model you use has magically a perfect indication if it might be wrong. So there's no right or wrong answer here. It depends on the setting, what you want to do. But I'm still curious to ask the audience. So let's do a show of hands. Who chooses the orange potion? Okay, who wants the pink potion? Okay, more people want the pink potion. That's good news for the talk. As I said, it depends really on your use case. For automation, for low stakes things, for coding maybe, you would of course prefer a lower error rate. The point rather I want to make is that the orange potion, at least in theory, we know how to make it. It's more data, improve the models, better training, whatever. How to make the pink potion is what we want to look at today. And especially as we will see for LLMs, there's not even a consensus what we want to be indicating here. So for the first 10, 15 minutes, I want to quickly go through the basics of uncertainty quantification to get everyone on the same page, but really only what's needed for the rest of the talk. And after that, we will start brewing increasingly complicated potions. So first, let me just set up some notation. And it wouldn't be a machine learning talk if there wasn't an MNIST example. So for MNIST, you have this input, and the input we will call X, which is here just a little image of a handwritten digit, and a model F, and then it produces some output y. We also have some what's called the ground truth. That's y star, which is what the person was actually trying to write. And this may or may not be the same as what the model has output. So finding out if it is the same, that's the question of uncertainty. And quantification means we need a number. So uncertainty quantification means we want some additional output, which is some number which says something about how reliable the output is compared to the ground truth. So if you're asking really fundamentally, from a machine learning perspective, what is an uncertainty? It's some measurement or some extraction from the probability distribution of ground truth outputs conditioned on everything else. So as a side note, for a venue like this, it's always difficult to get the right level of technical depth for the audience. So what I can promise, even if you don't read any equations, you can follow the talk and get something out of it. I have also included some more in-depth stuff for the machine learning experts in the audience. Okay, so I'm going to build up this recap slide. Let's add this. Uncertainty quantification means measuring something about the probability distribution. Whoa. Thank you. Measuring something about the probability distribution between the predicted values and the true values. Now, let's imagine we have something, we made something like this. How do we know if it's any good? Well, ideally, we would want it to be able to detect all the cases where the model makes an incorrect prediction. So I did this experiment to put on the slide. I sorted these MNIST predictions by low uncertainty and by high uncertainty. A green frame means it's predicted correctly, and a red frame means it's predicted incorrectly. And the question is, if we come up with some kind of uncertainty measurement, how well can we separate all the incorrect predictions to the right side? So that's called the ranking property. There's no universal term in literature. You can also call it just the error detection, maybe. And you measure this with the AUROC. If you've seen this, you know what it is. If you've never seen this, don't worry about it. It's just a number between 0 and 1, let's say, which tells you how well, if it's 1, it means you can perfectly separate all the incorrect predictions out based on the uncertainty. Okay, let's go to the recap slide. At this, how do we validate uncertainty measurement? By using the ranking property. Okay, we know what it is. We know how to check it. How do we make it? For this, let's go back to the MNIST example. So what most models, especially in deep learning, do, they don't just output a single label for the prediction. Rather, they output what's called a softmax vector, which is just a vector of scores, one score for each class, and they sum to 1. And the label with the highest score, that's the one you pick as a prediction. So why not just use this, right? The height of this bar as a measure of uncertainty. So rather, if we want to be precise, if the bar is higher, it becomes more certain. So let's do uncertainty is 1 minus the height of this bar, and we call this the confidence. So in this case, it's 1 minus 0.56. Okay, let's just imagine, how about for predictions which are 56% confident, right, because it's between 0 and 1, how about they're also correct 56% of the time? That would make the uncertainty much more useful, because we can tell something in absolute terms about the accuracy of the method in this particular example. And that's what's called the calibration property. So calibration measures, in the cases where it's 56% confident, is it actually correct 56% of the time? If, say, it's only correct 46% of the time, we call that a calibration error of 10%. So this calibration property is somewhat orthogonal to the ranking property. You can have a model which is perfectly calibrated, for example, by always just saying the average accuracy as the confidence. So calibration will be perfect. At the same time, it will be useless as an uncertainty measurement because you always just get the same uncertainty. So these are two different things we need to measure. Let's add it to the recap slide. So we looked at the calibration as a second way to validate uncertainty measurements. Specifically, it works for confidence. And for the case of a softmax output, we saw that the confidence is one possible way of doing uncertainty quantification. Let's also go back one. And this seems maybe difficult to do if you're just getting out these scores and are trying to achieve this calibration. However, for most training methods, or for most losses, in this case we would use binary cross-entropy loss, it will be, at least in theory, calibrated by default. And that's because the binary cross-entropy loss is what's called a proper scoring rule. And a proper scoring rule means a loss that if you use it to train, the score will be properly calibrated. And this will come up later also, so I wanted to mention this. Okay, I want to look at one more measurement for uncertainty quantification. That's called the information entropy. So just now, the confidence just looks at this one class. Instead, maybe we want some more general measure of how spread out is the softmax distribution. And this we can measure using what's called the information entropy. Many of you know this probably. So you just take each score and you do, it's called P, and then you do P log P and sum it over all classes. That's what's called the information entropy. This is not between 0 and 1. Unlike the confidence, it's between 0 and some number which depends on various factors, which we don't need to get into. Okay, let's add it. Information entropy, the second way of doing uncertainty quantification for softmax outputs. Finally, we've seen what uncertainty is, how to validate it, how to work it out. Where does it come from? There's two main sources of uncertainty, at least from the Bayesian perspective. That's firstly is called the epistemic uncertainty. I couldn't find a fitting MNIST example, so I made this new example. On the x-axis is x, right? The input. On the y-axis is what we want to predict. And we train on all these black points. And if we want to predict something in this region, it would be uncertain. And that's because we have too little data. So Greek, to know, means episteme. So epistemic uncertainty is lack of knowledge. This is reducible by just collecting more data. As we will see for LLMs, this can also mean collecting new data during test time. The other kind is on the right side of this example. It's called aleatoric uncertainty. Latin alea is the dice. And if you try to predict the number that comes up on a dice, you will also be uncertain. This is not due to lack of training data. Rather, it's because you're trying to predict something which is inherently random. So the same here. We have enough data. We could probably fit the underlying data generating process perfectly, but still, if we try to predict any individual point, our prediction would be uncertain, just because there's a lot of noise in the measurement. Let's add this to the recap slide. I mean, what's important to point out is aleatoric uncertainty is inherently irreducible. You can't do any improvements or anything that will reduce it. It's part of the problem, not of your method. Also relevant, we have here once again the information entropy, and you don't need to look at the whole formula, just squint your eyes, and you will see two black shapes, which means the formula falls apart. You can decompose the entropy into two parts, which is exactly the aleatoric and the epistemic uncertainty. If you're into Bayesian deep learning, you will get this, or maybe know it already. I mainly put this here to point out that these are real concepts that you can work out in theory and that you can point to in theory. It's not just vibe-based buzzwords. Because there has recently been some discourse, especially in LLM literature, about these terms. But at least from a Bayesian perspective, they have a hard definition. OK, let's edit. Sources of uncertainty, epistemic, aleatoric. And while I hydrate, you can look at these things again. This is all you're going to need for the rest of the talk. And you are also going to need all of this for the rest of the talk. "11 minutes. Hopefully, not so bad for the basics. So, going to LLMs, I wanted to have some example which is relatable and which we can follow through and look what different methods do. For the venue, most appropriate would be, of course, some kind of medical diagnosis. However, I don't have a medical background, so I couldn't find one. I did, however, recently come into the possession of a 15-year-old Skoda, which has also been having some issues that need diagnosing. So I ran this example. So this is a real problem and the real predictions. And the good news is I took it to the workshop. I have the ground truth on the printout, but I won't reveal it until the end of the talk to keep the suspense up. I ran this all on a local model, Gemma 3, which ran on this ThinkPad. So I asked, my 2011 Skoda Octavia makes a grinding sound when moving. What's the issue? And Gemma says, the wheel bearing is probably failing. I'm no expert, but it doesn't sound unreasonable. However, let's do a sanity check. Let's ask, something about my car feels weird. What's the issue? A worn wheel bearing is, yeah, OK. So this hopefully highlights the importance of uncertainty quantification, of having some measurement of how reliable any given output is, right? And not just having the text to go off. OK. Let's do the notation slide or the setting slide again that we had for MNIST. Nothing has changed. We still have an input, which is still called X. This is, in this case, just the prompt. You have the model, and the output is now not just one class. Rather, it's a string of tokens. So we'll call these, each token is S0, S1, and so on. And we get the whole sentence like this. Now, I was talking to my, actually, one side note, unlike MNIST, we can't just compare equality to the ground truth answer, right? For MNIST, we just had two numbers we can compare. It's a prediction the same, and we're done. Here, it's not so easy, because the workshop might say, the wheel bearing is destroyed, and then it's sort of subjective whether this answer was then correct or incorrect if you have nuances like this. In practice, for benchmarks, people just feed the output plus the ground truth into another LLM, and then ask, are these two statements the same? And then go off of that. I do think this introduces a lot of noise in the validation process, and it misses subtleties. And there's also some examples of this later on. OK, so I was talking to my father on the phone, telling him about the talk I was giving. He doesn't have a technical background. He's a retired German teacher. But he uses AI sometimes to ask about hobbies and so on. And I told him what uncertainty quantification is, why it's difficult to do for LLMs. And he said, just ask. Just ask in the chat, how confident are you 0 to 100%? And just use that. And that's a good idea, I thought. So I tried it out here. So to the system prompt, you just add something like, on a new line, add your confidence, et cetera, format it like this, and so on. Then you put in your question, and then this is the answer I got. Still the same answer, which is a good sign, and it says confidence 65%. I mean, again, it's a reasonable output. At least the model maintains some plausible deniability, whether it turns out to be wheel bearing or not. Now, I have to admit, it turns out my father was not the first person to come up with this. This is actually quite a well-known and widely used approach called verbalized confidence. And let's look at some results from literature, whether this works. So this is the benchmark humanities last exam, which is it's just like very specific and complicated questions, like translate this cuneiform tablets from ancient Babylonia into ancient Greek, things like this. So difficult questions. And you can see all the current models, they get accuracy around 50%. And they also get asked their confidence in this way I just showed. And look at the calibration error. It's basically worst case performance. To be accuracy 50% and calibration error 50%, it means you have to be saying I'm 100% sure every time, and you're only correct half of the times. So this really seems to work quite poorly. How can we explain this when it seemed to work okay for the Skoda just now? Well, it's exactly due to these sources of uncertainty. Humanities last exam is basically pure epistemic uncertainty, which is what you want for a benchmark, right? You want all the questions to be solvable exactly. You don't want uncertainty coming from ambiguous or random questions. And for these cases, seemingly LLMs really can't do this self-assessment. There is one paper which I included. It's a few years old now, but they did look at like more ambiguous questions, where aleatoric regime, and there they find it works fine actually. So this sort of mirrors our observation from just now. So we find this verbalized confidence is no use for epistemic uncertainty. It works fine, more or less, for aleatoric uncertainty. Just checking my notes to see we don't miss anything. Okay. Let's add this to the overview slide. This slide will stay with us for the rest of the talk. Each new method we talk about gets added to the slide. Verbalized confidence. If you are asking really from a machine learning perspective, what exactly are we quantifying here? You don't know. It's the LLM approach saying just Claude, take the wheel, do uncertainty quantification, and not worrying about the theory. It seems this is not good enough for us to have this really trustworthy and also work reliably. It seems we need something external. So for this, let's look at how the LLM generates this answer. Although, I mean, many people probably know this, but I still need to set up the slide for later use. So how it works is you have this input, and then the LLM outputs a softmax vector over possible tokens, and they output only one, generally speaking. So here, the first word of the answer could be the or your, with scores of 52% and 37%. Then you pick one. There's different ways to sample this. Generally, you pick a token with a probability proportional to its score. So we pick the, then you append this to the input, and you feed it in again, and you generate softmax for the next token. So wheel, then, okay, we pick wheel, it has the highest probability, and so on. So you keep doing this, the wheel bearing is, and so forth. That's how it works. So, I mean, each token still is a softmax vector. It doesn't look that different from what we had with MNIST. The question? No. The question is just we have this strange iterative procedure and randomly selecting tokens, and we don't really know how to deal with this. What if we could somehow condense the whole answer into just one token? Then we could use the same methods that we had for MNIST. So this method exists. It's called the p-true. So how you do it is, firstly, you just generate the answer as before, nothing changes. And then step 2, you dress it up a little as a quiz. So you say, someone asked this question, someone else gave this answer. Is the proposed diagnosis true or false? Answer, colon. And then you just do one token. OK, now you can see here in the softmax output, you have true, then you have some more stuff which isn't ideal, but then you have false down here, right? So now we can do what we did for MNIST. Now we just have a single softmax vector of scores, which we can evaluate however we want. Specifically, if we want the confidence, we would just take, P for true and the probability for false, and then, renormalize. We get the 95% confidence for this case. So it seems a little high, and it's, of course, also way higher than the 65% we got first. If you look at the literature, the authors who introduced it, for them, it worked fine. So what's the problem? The problem is that the paper who did it came out 2022. And back then, the models they used it with were just maximum likelihood trained autoregressive transformers. Any models you get these days who can do actual, real-world useful question answering have various post-training steps. That means after they're just trained as a classical maximum likelihood model, they do some reinforcement learning, fine-tuning, integrate some human feedback, and so on. And this post-training process is not a proper scoring rule. That means the scores that you get are not properly calibrated, whereas for standard maximum likelihood model, they should be, in theory. That's why this doesn't really work anymore. There are, of course, in the meantime, have been dozens of engineering papers trying different things to fix this. And you can get a certain way, adding extra fine-tuning steps only on this, like fine-tuning for the uncertainty calibration. You can also come up with different kinds of quizzes that work for more kinds of questions, like generating multiple choice tests and then having D other, and then going off that. But generally, 2026, this method doesn't get very far. Imagine for big tasks with 2,000 lines of Python code and then saying the quiz question is, does the above code have a bug or not? It's sort of limited usefulness above this very short-term questions. Let's add it to the overview slide regardless. P true does uncertainty quantification on a single token. And it works basically, but it's not good enough for us. So let's try to find something which really takes the whole answer into account. And for this, let's go back to the information entropy we looked at. We can just compute it for every token choice, right? So information entropy for this softmax vector, information entropy here, and so on and so forth. I also added the rest of the sentence to the slide this time. And then you have different ways of accumulating this. There's many different engineering papers how best to do this. In this case, let's just take the average. So I have to point out, don't get it confused. This isn't the information entropy of the output string as a whole. For that, we would need to do this p log p sum over all possible outputs. That's astronomically many outputs. You cannot do it. So this is more just a heuristic, but it doesn't mean it can't work. However, in this case, let's look at where the contributions actually come from. So that's, if we go back one slide, here we get a big contribution from the first token. That's whether it's supposed to say the wheel bearing or your wheel bearing. Then this token 1 and token 2 is where the actual answer happens. Wheel bearing, brake pads, starter motor, wheel speed sensor, and so all the answers actually happening in these two tokens, and they contribute nothing to the uncertainty. Then second half of the sentence, same thing. Failing wheel bearing or worn wheel bearing, it's probably failing or likely failing. All this kind of stuff contributes all the entropy and not the actual answer we care about. You might say, well, it's just because there's low uncertainty. I mean, sure, that might be an argument, but even if these contributed, it will be extremely noisy signal, just because all the other parts of the sentence, how to phrase it exactly, which words to use, all contribute lots of entropy, which you can't really disentangle from the entropy that comes from the actual answer you want to hear. This doesn't mean this is a bad method. There is one setting where this works pretty well, and that's for hallucination detection, which, I mean, it's a buzzword. It's really just a question of epistemic uncertainty detection, where the model gets a question it's not trained on and starts just making stuff up freely. And if you check those cases, you do see a very sharp uptick in average token entropy. So it works fine for this, but for these kind of questions, caring about the content as such and aleatoric domain, it really doesn't work. Let's add it to the list. Token entropy, uncertainty quantification on the entire output string. Okay, drinking break. Okay, so we've gone from not knowing what we're quantifying to uncertainty quantification on a single token to uncertainty quantification on a single string. And we've discovered what we really want is to quantify the semantic content of the output. We really can't do this with just a single output string because sort of as soon as it says wheel, it's locked in and the next word will be bearing and so on. So we have no other way than to sample. And I did this. It took 20 minutes to generate 32 answers. You do need to tweak the parameters for the sampler a little bit to get varied answers. You don't have to read them all. I did that work. So that's the first step, is just generate 32 answers. The second step is to cluster them. So all the blue ones, it says something about wheel bearing. All the orange ones, it says something about CV joint. And then you just throw away all of the answers. You just keep one representative answer per cluster. And then you get this kind of pie chart. So 88% of the answers were it's a wheel bearing. 12% of the answers were it's a CV joint. And now you can do the same toolkit as we had for MNIST, compute the entropy, compute the confidence, 88%, and so on, to get an uncertainty estimate like this. Now, maybe if you were looking sharply, you saw mistakes on the previous slide. For example, a lot of the time it says like it's the passenger side wheel bearing, it's the driver side wheel bearing. This all got clustered into the same cluster. So that's because how this works is by using some kind of embedding models, metric learning, another LLM. There's various approaches, and this is imperfect and will miss subtleties. So I left in the mistake just to demonstrate that the clustering isn't infallible. Let's also compare to the vague question at the start, where we just said something feels weird. And you can see it has like 20 different clusters. It comes up with 20 semantically distinct answers. The wheel bearing answer that we got that we weren't sure about is in here, but only 16%, and everything else has almost similar weight. Okay, let's add this to the overview slide. So this is called semantic uncertainty. You're doing not uncertainty quantification on any exact output, rather on the semantic meaning. This is, for many cases, like the go-to method to use. Gets the best results, generally speaking, over different kinds of uncertainty in different settings. There are extensions, and some of these I linked as references on the previous slide. Extending this to cases where it isn't a simple question-answer setting, but rather things like summarization or code generation, where you can't really do distinct clusters. You can still analyze a graph of semantic connectivity and then extract some uncertainty measures from this. But basically, this all works quite similar. Just generate 20 answers and do some semantic evaluation on that. Another side note, just because everyone is talking about conformal prediction, maybe, I don't know. depends on your hobbies. But there was also a talk at this venue I saw. It's a few years back now, but was a talk on conformal predictions, which is very similar. It's just about generating multiple answers with some like coverage guarantees. So you can say it's 90% guaranteed that it's one of these answers. You can do this for LLMs. I also linked one of the papers doing this, but it deserves its own talk, I think, because it's a conformal prediction is a big topic. But it works the same way: sample and then do some kind of semantic analysis on that. Okay, so everything up to here was basically, I mean, not a hugely realistic setting. It was just this closed question-answer type setting. But at least everything since 2024 for practical use has been what's called reasoning models. So I don't know if you use ChatGPT, you get this little animation at the top where it says thinking. So the LLM is outputting some tokens and then arriving at the final answer. So the question would be, for these kind of state-of-the-art models, shouldn't we somehow include the uncertainty of the reasoning process, the uncertainty in all the steps needed to arrive at the final answer? There are like dozens of engineering papers trying to do this manually. It's all very clever ideas. So, taking any of these methods we've seen so far and using them in the reasoning process, either to identify steps where things might go wrong, sampling alternatives, or identifying high uncertainty states and then going back to previous steps where it looked better and retrying, things like this. And this generally also works. It's not what I wanted to talk about so much, because methodologically it's nothing super new compared to what we've already looked at. Instead, I want to look at a line of papers which came out over the last few years, which do an information theoretic analysis of the reasoning process. So this is called like the self-Bayesian setting, because the model starts out, if you ask it for an answer right away, it's very uncertain. And then through these reasoning steps, without getting any new information externally, it like reduces this uncertainty. So it does generate information somehow from just talking. And so for this example, we need to specifically look at cases where it starts out along the wrong path and then corrects itself. And you find generally there's like two categories of these corrections. So the first one is called the procedural channel. It's called that because the LLM is just going through the procedure of solving the equations step by step. And then at some point it meets a contradiction. So I took one trace, it works out, solves many like quadratic equations and so on, gets out x equals 0. And then it finds, however, substituting x equals 0 violates, this is not a spelling mistake, this is in the actual reasoning trace, but it violates a condition given in the problem that the solution must be larger than pi. So this is called the corrections on the procedural channel. And then there's also, this works for any LLM. This even works for non-reasoning LLMs if you prompt them with chain of thought. So you just tell them how to reason and do it. The second channel is called the epistemic channel. And this only happens in LLMs which were reinforcement learning trained on the reasoning process. For this case, it just spontaneously decides, you know what, I don't like the look of this approach. Let's try something else. So in this case, I tried it myself. The question, it was an algebra problem. I couldn't do it, but the Quen 35b could. So it starts, thinking through how to solve the problem, and then it says, you know what, finding the determinant directly from these equations might not be straightforward. And without having tried it, or without having met any explicit contradiction, it says, you know what, let's instead look at, and then it tries a different approach from the different sides and solves the problem successfully. notes check. Okay. I mean, the research question is just some artifact, like it's randomly picking a different token and then going on a different trajectory, or some other spurious artifact. But the research points towards the fact that this is not the case, and that this is actually surface level verbalization of actual, intrinsically represented epistemic uncertainty. So we saw earlier with humanities last exam, in general, LLMs can't do this. They can't estimate their own epistemic uncertainty. However, if you do reinforcement learning on just the reasoning part, it emerges just naturally, right, without having to enforce this in any way. So that's sort of the big research finding of these recent series of papers, also some more which didn't fit, that epistemic uncertainty detection emerges just from reasoning reinforcement learning. Kim et al. 2026, their interpretation is that this is basically a question of allocation. So it's allocating tokens between these procedural steps of actually explicitly solving the equations, which you still need to do, and trying different approaches. And in a fixed token budget, you have to allocate efficiently. And their theory is that this mechanism arises through this. I have another perspective coming up towards the end. So in general, there's a lot to say about this, which doesn't fit the time constraint. But do read the papers if you're interested. You're asking why I bring this up, even though there wasn't any quantification per se. That's basically to point out that, especially for these long-form, compositional, complex tasks, using some kind of uncertainty detection and making allocations, making decisions based on this uncertainty is so important that even if you don't include it, reinforcement learning will reinvent it by itself. Let's add it to the overview slide. So reasoning uncertainty quantification, in some way, extrinsic or natural uncertainty quantification on the trajectory to get to the answer. So you might be wondering two things. That's firstly, if this is what it looks like for reasoning, how about like agents or agentic settings where the LLM both does reasoning, then it does something, maybe some database query, it gets in the data, then it does more reasoning based on that observation, and so on. And the second question you might be asking is, where was the Skoda on the previous slide? Don't worry, it's coming back. And we need this example. It's going somewhere, I promise. So agentic setting means acting in the world. So let's also act on the grinding noise and see what solution we can find. One option would be take it to the workshop. If we take it in, it is the wheel bearing. It costs us 1,000 euros, they said. If it's something else, on average, it's also 1,000 euros, just for the sake of the argument. Now, for the wheel bearings, it's not that complicated to do yourself. If you watch some YouTube videos, buy like cheap Chinese replacement wheel bearings, like rent a workshop, you can do it for half easily, I've been told. But so if it is the wheel bearings, we save half. If it's not the wheel bearings, then we've taken apart the whole car, bought replacement parts which we don't need, and we still have to take it to the workshop. So it will still cost 1,000 plus the 500 we wasted on top. Okay, so now uncertainty quantification helps us, know what we need to do. Let's just take the 65% confidence that we had at the start at face value and use this to compute our Bayesian expected values. So if we just take it to the workshop blind, I mean, it's going to be 1,000 either way, 1,000 expected value. If we DIY, 850 expected value. Okay, so this is cheaper, this is what we should go for. However, there's a third option. So the Kfz Meisterwerkstatt Kahn, they offer for 100 euros to diagnose your problem. They don't fix anything, it's just 100 euros for nothing from this perspective. However, instead of having to commit to row 1 or row 2 in advance, we could get the diagnosis, and after that, pick the cheapest option from the column depending what the diagnosis is. So let's, in advance, even before getting the diagnosis, we can still use the 65% to get the expected value for this. So it's 100 for the diagnosis, and then 65% is cheap, 35% we end up taking to the workshop directly. This ends up actually, even though we spend 100 euros extra that didn't fix anything, we end up 75 cheaper in terms of expected value. This is what's called the value of information. So you can actually quantify this, how much did this information help us make better decisions and get better expected value, even though the information itself, didn't bring any actions with it. We can highlight the importance of the uncertainty quantification for this. Let's do like a sensitivity analysis. So on the x-axis is the confidence that it is the wheel bearings. On the y-axis is the expected cost. And I put the 3 strategies. And you can see, if it's like below 20% confidence that it's the wheel bearings, it's cheapest to just take it to the workshop and not bother. If it's more than 80% sure, you should first try it yourself. On average, the diagnosis won't be worth it. If it's between 20 and 80%, the cheapest option is to spend 100 extra just to get the diagnosis. So the 65 is here. It also highlights why this calibration and so on is important, because if it said, I'm 95% sure it's the wheel bearings, and actually it was only 10% correct, like many of these models were, we saw, then we decide here on the green line, and then we're actually over here in real life, it will be very expensive. I mean, unnecessarily so. Okay, how does this relate to LLM agents? I just screenshotted some headlines I came across. I accidentally burned $6,000 of Claude usage, and then 3 examples also where different AI agents deleted very important stuff. So it does seem they would profit from this kind of analysis, right? When is it worth investing just a little bit more time or a little bit more tokens to double check if the outcome might be catastrophic otherwise? And at the same time, if you're in the habit of using Claude Code, you know that Claude Code, and that's where this headline comes from, obsessively double or triple checks everything. It reads all the files, it runs all the tests, it looks at all the test outputs, even if it just changes whatever, something small, which probably won't cause problems or it wouldn't matter otherwise. So using uncertainty quantification and using this kind of value of information and so on, really it's possible to tell what to do and how to make good decisions. And in fact, decision theory has been around for much more than 50 years, and exactly formalize this and knowing how uncertain you should be about what and when to get information and when not. So if we take standard agents, Claude Code and so on, they mostly follow like the React framework, which is I think the last one of the references. It's just instructions that someone typed out. It says if always check and so on. And it basically does the cycle. It observes, like it looks at the file, it looks at your prompt, it assesses, it thinks about what to do, it decides on an action, it does it, and then it keeps going. And so uncertainty quantification slots in. On the one hand, if it's very uncertain, you might decide it's most efficient to gather more information. This also might be the self-Bayesian process of gathering information by thinking about it longer. Also in the decision, as we saw for the 3 strategies for getting the Skoda fixed, what to do what's the best decision will also relate to this uncertainty. So as I said, in decision theory, this has all been formalized. The things to look for here is dynamic Bayesian networks and partially observable Markov decision processes. That's a mouthful. I've included this, it's not really a book, it's just 50 pages from 1998, which I can recommend on the topic. So here they set everything up already, and they have rules and algorithms how to actually, when to gather information, what to do, how to decide based, on uncertainty. There are also publications doing this for LLM agents, although it's a little, it's early on. Here you can see the setup for a dynamic Bayesian network. You don't need to read the details. It's the task is to change a flight reservation, and you have nodes in your Bayesian network about the observations, the context, the actions, and you can work all this out very rigorously, and develop guarantees and strategies to actually make good decisions and not end up with negative examples on Reddit of people wasting 6,000 euros because Claude checked the unit tests too many times. Let's add it to the overview slide. Agentic uncertainty quantification means uncertainty quantifications on or in a series of decisions in the world. And by in the world, I mean in the computer. Okay, that's it. That's all I wanted to cover. I have 2 minutes and 40 seconds left. We will find out what was the actual issue. Plot twist, it has 20 things wrong with it. So I phoned up, I said, it's fine, okay, but what specifically was making the grinding sound? Guess what they said? The wheel bearings. It was them all along. The rest is what's known as unknown unknowns, stuff we didn't ask about and thus couldn't even quantify the uncertainty of. And this leads nicely onto the final slide of caveats and open problems. So firstly, things I skipped. There are several approaches, sort of traditional approaches from Bayesian deep learning. Ensembles, so LoRa ensembles is a way of doing this for cheap. Things like Monte Carlo dropout. There's also what's called a BLORA, which is adapting an existing large language model to be a Bayesian large language model using the same kind of formalism as LoRa's. Then I mentioned it, but conformal prediction. This is especially relevant because, as we saw, all this post-training and reinforcement learning ruins the proper scoring rules and ruins the output probabilities. And conformal prediction doesn't rely on this and works anyway. So I think that's one reason why it's sort of important in the LLM space. And then finally, there's various kinds of I'll call it learned uncertainty quantification, where you have either an additional head on the network, which is fine-tuned only on predicting confidence estimates. Also additional small networks, which get in some representations and try to predict uncertainty. And many more, of course, which didn't even make it onto this slide. There's some big open problems which I don't see going away. That's firstly, as I also just said, the reinforcement learning and the post-training ruins the softmax probabilities. And so, many years of theory that I spent doing at Uli's lab for uncertainty quantification on maximum likelihood models no longer applies that easily for LLMs, and you have to find ways around that. Secondly, I'm also unhappy looking at the state of evaluation. It's becoming tough to come up with benchmarks which measure anything meaningful. And even when people do the evaluation, the reported metrics and so on are vague. There's no consensus on what to measure exactly and so forth. Finally, things which I may have come over as over-optimistic. none of the methods is plug and play. So you saw all of them sometimes don't work. If you go to API for OpenAI or Anthropic, they don't give you the token probabilities, so you can't use all of these methods if you want the cutting-edge proprietary models. And we also saw all of these methods very domain-dependent, work for some kinds of uncertainty, don't work for others. So if you have any questions, do ask them now. If it's an extremely complicated question, here's my email for bookings. And I mean, if you allow me these 10 more seconds, also do pass on my info if you know people who might need a workshop on this kind of stuff or are currently in the process of adopting LLMs and want input, how to make it robust and trustworthy and so on. Okay, that's it.